Okay. All right. Welcome everybody to the first iteration of GOCC for the semester. This week we have Chris O'Neill giving an expository talk talking about classifying numerical semigroups using polyhedral geometry. Before we begin, I'd like to mention our community guidelines. So we are all learning. Everyone has something to contribute, and no one has all the answers. So on that note, take it away, Chris.
All right. Excuse me. Thank you all. Thank you for the invitation to speak here. And thank you for accommodating the slightly unusual start time. Unfortunately, I teach right when the normally scheduled time would sort of be ending. And in between this talk and teaching, I have to change both buildings and headspaces. So this will give me a little time to do that. Hopefully, the different start time won't sort of cause too many issues. So it does feel a little bit funny calling this an expository talk, though I think that is technically accurate. It is covering things that have been proven within the last sort of decade or so, and in particular, it's a project that has been kind of evolving over that time. For me personally, I guess I'm not sure if I'm still technically early career, but this was one of the sort of the first kind of long-term projects that I got to see evolve over time and the sort of machinery that's built up as a result. And so what I wanted to talk about today was what some of that machinery is. It kind of sits in this area between combinatorics, algebra, and some polyhedral geometry, and sort of a neat way that these things have been playing together. And so that's sort of the story I want to tell you about today. So, excuse me. A numerical semigroup is a subset of the non-negative integers that's closed under addition and has finite complement. Typically, we specify a numerical semigroup by giving a list of generators. In this case, this would be 6, 9, and 20. So this would be all of the non-negative integers you can get by adding 6s, 9s, and 20s together in all different ways. Right? So we see in here we get 0 by adding nothing. 6 and 9 are both generators. 12, we get a 6 plus 6. 15, we get a 6 plus 9. 18 is the first element that we can get in two different ways, right? As 6 plus 6 plus 6, or as 9 plus 9. And what we find is as we go further out here, because there's more ways to add these together, we start to see less and less integers being omitted. And what you'll find here, for instance, that 43 is the last integer that's missing here. Everything afterwards, 44, 45, everything higher, there's some way to add 6s, 9s, and 20s together to get you exactly that value. So this is my personal favorite numerical semigroup. It's known as the McNugget semigroup because for a long time, McDonald's sold chicken nuggets in packs of 6, 9, and 20. So an integer lies in this semigroup if you can buy exactly that many chicken nuggets using those pack sizes, right? So for instance, if you walked into McDonald's and you were craving exactly 43 chicken nuggets, you're out of luck. There's no way to perfectly satiate your appetite with those pack sizes. But if you were craving 44, 45, or anything higher, there's some combination of packs that will get you exactly that number of McNuggets. Now, suppose McDonald's decided to add a couple of new pack sizes, like an 18 pack and a 32 pack onto their existing pack sizes. Effectively, this would end up not really changing the semigroup because 18 we were already able to get as, say, for instance, 6 plus 6 plus 6, and 32 we were able to get as 20 plus a couple of 6 packs. So in particular, we get back the same semigroup, the McNugget semigroup. And so one kind of nice fact here, every numerical semigroup has a unique set of minimal generators. In particular, this is a minimal generating set, both sort of minimal with respect to cardinality and with respect to containment. What this means is that every element of the semigroup either is or is not a minimal generator, based on whether it can be written as a sum of strictly smaller elements. So it's kind of a nice attribute. Here we'll be using that kind of throughout the talk. I try to keep running terminology or variable usage low in a talk whenever possible, but lowercase m, which we're going to use to denote the smallest generator, is going to appear on pretty much every slide of this talk. So that's what lowercase m is going to mean, either the smallest positive element or equivalently the smallest generator. All right, so given a numerical semigroup, Sorry. One more thing I'll mention here. The word multiplicity is used here because of one of the places where numerical semigroups sort of naturally arise. Out of the singularities of a certain type of algebraic curve, you can build a numerical semigroup. This is one of like several different places that numerical semigroups kind of independently show up. And originally, each of those places kind of had their own terminology for different attributes of the semigroup. And it turns out the algebraic curve setting is where the word multiplicity, this term, sort of won out, sort of the battle for history in some fashion. So it's called the multiplicity, but you don't have to know anything about algebraic curves. This really is just a word we use for lowercase m now. Is sort of the point. All right. So fix a numerical semigroup whose smallest generator is M. We'll define the apiary set of S in this way. It's the set of elements of S such that when you subtract M, it takes you outside of S. So this definition is nice in that it is very compact, does not use a lot of ink, but it is masking some really nice structure for this set. So for example, the apiary set of the McNugget semigroup consists of these 6 integers, and they appear to be written in kind of a weird order, but what you'll notice is that there's exactly one in each equivalence class, mod 6. Here 6 is our value for M. And the reason for this, if we take our favorite mod class, let's say 4 mod 6, so take all the positive integers that are equivalent to 4 mod 6, because S is closed under addition, once something in this equivalence class is in S, you can get everything after that in the equivalence by just adding a bunch of copies of 6, right? So effectively what's happening, the apiary set is sort of recording within each mod class when you go from being outside the semigroup to when you're inside the semigroup. And so just to sort of record those observations, there's always exactly M elements in the apiary set, and each one is in a distinct equivalence class, mod M. So I didn't say this before, but if at any point there are questions, please stop me to ask. I'm perfectly happy to go on tangents and things. So the apiary set is very nice, and it shows up a lot when you look at numerical semigroups. So for example, if you wanted to do like a quick membership test, so someone walks up to you on the street, hands you a number and says, can I buy exactly this many chicken nuggets using packs of 6, 9, and 20? Well, if you know the apiary set for the McNugget semigroup, all you have to do is take that number n, check which equivalence class it's in, mod, in that case, mod 6, and then check m is n larger than that apiary set element. So it makes checking whether something's in a semigroup or not kind of quick. Additionally, there's several quantities that come up a lot when studying numerical semigroups that are closely related to the apiary set. So for example, the Frobenius number, which is the largest gap. So for the McNugget semigroup, that was that 43 that we saw. That you can obtain essentially from the maximum element of the apiary set. So Frobenius was one of the first people to study numerical semigroups, and he posed this question about the largest gap. Unfortunately, he lived too early to be thinking about chicken McNuggets. For him, the generators were coin denominations. And so his question was, what's the largest value you can't make even change for using those coin denominations? He found a really nice formula when there's only 2 generators. In particular, it's their product minus their sum. It turns out when you've got 3 minimal generators, there's a sort of fast algorithm to find the Frobenius number. For those that are computationally oriented, for fast, you can think Euclidean algorithm fast. But once you got 4 or more generators, this is an NP something problem. It is sort of a known difficult problem to compute the Frobenius number from a given list of generators. Similarly, if you want to know how many positive integers lie outside of your semigroup, that's the number of gaps. We call this the genus. This formula requires a little bit more ink, but from a computational perspective, this is fairly quick. In particular, if someone just walks up to you on the street, hands you a list of generators, computing this value is again NP something big. But if you happen to already know the apiary set, you can recover it rather quickly. And in fact, it turns out if you want to compute the Frobenius number or you want to compute the genus, most known algorithms for doing this effectively have you compute the apiary set with roughly the same sort of runtime. And so we tend to use apiary sets as kind of a one-stop shop for computation. If you want to be studying any one of these things, you might, there we go. Oh no, that's permanent. Okay. You might, you, and then you get access to that and anything else sort of that you want. So that's sort of, apiary sets are kind of central when we're studying these things. All right. So what I'd like to do now is play the inverse game here. So someone walks up to you on the street, hands you a finite set of integers, and says, "Is this the apiary set of some numerical semigroup?" Well, based on what we just saw, the integers better lie in different equivalents. So okay, m would have to be 5, right? Because there's 5 integers here, and these would better lie in distinct equivalence classes mod 5. And sure enough, they do. However, it turns out this is not the apiary set of a numerical semigroup, and the problem here is the 23. In particular, each of these integers would have to be an element of the numerical semigroup in question. So 11 and 7 would both have to be in there. That means that their sum, which is 18, would have to be in there. But 18 is strictly smaller than 23, right? And in order for this to be the apiary set, 23 is supposed to be the smallest element. That's 3 mod 5, but 18 is strictly smaller than that. So that makes this not the apiary set of a numerical semigroup, right? Similarly here, we were handed this 6-element set, right? M would have to be 6. These all lie in different equivalence classes. We end up with a similar issue, this time coming from the last 3 values. In particular, if we have 10 and 11 are in a semigroup S, then their sum, which is 21, would have to live in S as well, but that's strictly smaller than the element that we're sort of claiming is the smallest that's equivalent to 3 mod 6. And so this is, again, not the apiary set of a numerical semigroup. Now, it turns out, it's perhaps a little bit surprising, this is essentially the only restriction to being an apiary set. Again, as long as your elements are in distinct equivalence classes mod M, and each of them is strictly larger than M itself, so that M is indeed the smallest positive element, then the only other things you have to check are these inequalities. So if you add a sub I and a sub j, these give you an element of the purported semigroup that is equivalent to I plus j mod M, and so that better be at least as big as the thing that we're claiming is the smallest in that equivalence class. And so we're going to keep having to take 2 cases every time we do addition and subscripts. We're going to view the subscripts as being elements of Z mod M. So in particular, this I plus j here is happening modulo M, right? That's why up here, for instance, we had A4 and A5 that gave us something that's equivalent to 3 mod 6. So we're sort of, subscripts are living in Z mod M. All right, so far this talk has all been very algebraic, but this is where geometry can sort of enter the picture. We now have a list of linear inequalities, and those we can use to define a nice polyhedral cone. And this cone is particularly nice in that each numerical semigroup with smallest generator M corresponds to an integer point inside of this cone, right? You just take your semigroup, you compute its apiary set, line the elements of that up based on their equivalence class. That point lives inside of this cone. And so, for example, here, if we look at m equals 3, this is going to be, the Kunz cone is going to be a 2-dimensional cone. And we end up with 2 inequalities here. One of them is a1 plus a1 greater than or equal to a2. The other one is a2 plus a2 greater than or equal to a1. And so this point here, which is 7 comma 5, is going to correspond to the numerical semigroup generated by 3, 5, and 7, right? 3 has to be a minimal generator because that's our value for M. And then the rest of the apiary set needs to be 7 and 5, and those both end up being minimal generators. Similarly, if we take this point up here on the sort of top bounding ray, that's the point 4 comma 8. This time the generators end up being just 3 and 4 because 8 we can get as 4 plus 4. And so one thing I'll point out here, this first semigroup example, oops, there we go. This first semigroup example was in the relative interior of the cone. We ended up needing 3 minimal generators, but this one is on the boundary we end up needing only 2 minimal generators. This turns out to not be a coincidence, and we'll see why in a little bit later in this talk. So for m equals 4, we have to kick things up a dimension to R3. We end up with 4 defining inequalities. So this is a 3-dimensional cone with a quadrilateral cross-section. In fact, that cross-section turns out to be a kite. It has sort of front-to-back symmetry here that you can see if you back. Sort of unique automorphism or non-trivial automorphism of Z mod 4. So the symmetries of this thing are going to be somehow coming from automorphisms of Z mod M. All right. And again, each numerical semigroup whose smallest generator is 4 is going to correspond to a point somewhere inside of here. Maybe it's in the relative interior. Maybe it's on this kind of back left facet back there. Maybe it's sitting on this ray, but somewhere in there will be a point that corresponds to that semigroup. All right. So the question I want us to think about then is when do 2 numerical semigroups live in the relative interior of the same face? And so what I first want to talk about is why this is an interesting question. And the motivation for this comes from the study of what are sometimes called parameter spaces, sometimes called moduli spaces. And the idea here is, so again, this is sort of a philosophical idea. If there's some mathematical gadget you want to study, maybe this is a family of groups, maybe it's a family of algebraic varieties or certain topological spaces. You want to study those. One way to do that is locate a space in which each of those things you want to study corresponds to a point, and where small changes in that object correspond to small movements in that space. So you start by locating such a space. That's what we call a parameter space. And then you let the geometric or topological structure of that space inform how you should be studying these objects you care about. As kind of an entry-level example, suppose we wanted to study n by n real invertible matrices. Well, how can we turn an n by n real matrix into a point? Well, we could just sort of stretch it out to make it a length n squared vector. And now each of these matrices corresponds to a point inside of here. And if you study that as a topological subspace of r to the n squared, what you'll find is that you have 2 connected components, one consisting of matrices with positive determinant, the other consisting of matrices with negative determinant. Now, if you spend some time studying real invertible matrices, this is perhaps not terribly surprising, but one way to think about this, this is effectively handing you on a silver platter the determinant as an important quantity when studying invertible matrices. This is essentially the philosophy here. You build this space, you then look at the structure of that space, and you let that tell you what you should be, how you should be studying the objects you actually care about. Now, what's strictly more interesting, in my unbiased opinion, than real invertible matrices, that's numerical semigroups. And so what can we use as a parameter space? Well, we have this family of cones we just saw, where each numerical semigroup, at least whose smallest generator is m, corresponds to a point somewhere inside of that cone. All right, what's the geometric structure? Well, if we look at face structure, right, this is effectively partitioning all of the whole numerical semigroup, the smallest generator is m, into finite pieces, right? So for example, if your smallest generator is 3, there's still infinitely many possible numerical groups. Your second generator can be non-multiple 3, larger than 3, but no spaces. In fact, vertex, because 0, 0 doesn't correspond to semigroup, so is partitioning the set of all numerical semigroups, smallest generator is 3, into 3 different sort of equivalence classes. What do semigroups in the same, that end up in the same face, have in common with one another? And so that's sort of the question we want to look at. And so just sort of thinking about what this face structure looks like as m increases, right? So when m is 3, cone. When m is 4, we got this 3-dimensional cone, and we said this has a quadrilateral cross-section. In particular, to think about the face structure of this cone, it really sort of suffices to think about the face structure of the cross section, right? That takes us from a three-dimensional cone down to just a quadrilateral. And the only face we're losing in doing that is the vertex at the bottom, which doesn't correspond to a semigroup anyway. This is kind of a nice visualization tool, and it lets us reach a little bit beyond our sort of normal comfort zone for geometric visualization, right? So when m equals 5, the Kunz cone lives in 4 dimensions. But if we take a cross section of that, that gives us a 3-dimensional polytope. And it turns out its cross section looks like this. Each vertex here corresponds to a ray, an extremal ray, back up in the original cone. Each sort of flat 2-dimensional facet of this corresponds to one of the inequalities defining the original cone. By the way, the name of this shape, this is a gyrobifastigium. Took me quite a bit of practice to learn this word. Where that term comes from, you can essentially build this by taking 2 triangular prisms and gluing them along one of the sort of, let's say, square rectangular faces, but with a twist, right? So the one on the right is sort of twisted 90 degrees before we glue. So gyrobifastigium. All right. So it turns out the thing that governs when 2 semigroups end up in the same face of the Kunz cone is sort of entirely poset theoretic. So we'll define the following poset. It's what we call the apiary poset. The ground set of this poset is going to be the apiary set of your semigroup, and you're going to partially order in such a way that one element lives above another if their difference is in the semigroup. And it turns out this is actually equivalent to requiring their difference to be in the apiary set. Right, so down here we have a couple of examples. Your semigroup is generated by 4, 10, and 13. Well, 10 and 13 both end up in the apiary set, and that last element ends up being 23. That's sort of the smallest way to get to 3 mod 4. From 1 mod 4 and 2 mod 4, as you add those together, you get 23. And so this is the poset we end up getting. In particular, 23 is above 13 because their difference is 10. 23 is above 10 because their difference is 13. But 13 and 10 are incomparable because 13 minus 10 is 3, which is not in the semigroup. So we get this poset structure here. Versus over here, if we have just 4 and 13 as minimal generators, then the remaining apiary set elements essentially have to just be multiples of 13. Because notice, to get the other elements here, all we can do is add 4s and 13s together, but adding 4s doesn't change our mod class. So the only way to get over here is to add 13 to itself over and over. And so the poset we end up getting ends up being a total ordering, working out multiples of 13. So this is the apiary poset. Now, if we take 2 semigroups, here we have m equals 6. This one is familiar. This is the McNugget semigroup. Here's one that I've chosen to live in the same face of C6. So remember, C6, this is a 5-dimensional cone. It turns out the McNugget semigroup lives in a 2-dimensional face of that cone. S prime is another semigroup in that same face. If we draw their apiary posets, we see they have really similar structure. And in fact, if we blur our eyes a little bit so that we can't quite read the labels, all we can read is their mod classes, mod 6, we get exactly the same poset. We're going to call this the Kunz poset of S, right? So to get this from S, we compute the apiary set. We build the apiary poset using the relation on the previous slide, right? Just when the one element's above another, if there are differences in the semigroup. And then once we built this poset, we replace each element of the ground set with its equivalent class, mod M. So that's the Kunz poset. Turns out this is exactly the thing that tells us when 2 semigroups live in the interior of the same face. It's when they have exactly the same Kunz poset. And in fact, you can essentially read off the relations in this poset from what we call the facet description of that face. So one way to sort of describe a given face of a cone is to list out the inequalities where that face you have to sort of satisfy equality. So the intersection of the different facets that give you that face. And each facet here essentially gives us a relation, right? So for instance here, A5 equals A2 plus A3, right? This would just be a greater than or equal to for the cone, but for this face, we have an equality. What that's saying is that A5 minus A3 equals A2. That tells us 3 needs to be below 5, right? Similarly, A5 minus A2 equals A3. That tells us 2 needs to be below 5. So these are really telling us exactly what the relations are in this poset. And notice it's not just cover relations either. So like we've got, where is this here? 3 precedes 1, right? That's not a cover relation. That's an actual honest to goodness relation. Or I shouldn't say that. It is not a cover relation, but it's still a relation, right? And so that is also coming from the facet here, or from one of the facets. And so, but yeah, this gives you a complete list of all of the relations except for the fact that we end up with 0 at the bottom of everything, right? None of these end up involving 0, but every other relation somehow comes from one of the facets containing the face corresponding to, or containing the point corresponding to the semigroup. All right, so that sort of settles the question of when do two numerical semigroups live in the relative interior of the same face of this cone? And the answer turns out to be combinatorial, which is nice. Here, if we sort of revisit m equals 3 and m equals 4, we've got each of the sort of Kunz posets that can arise showing up here. So like for m equals 3, if you're on the interior, then A1 and A2 end up being incomparable in the a priori poset. If you end up on one of the extremal rays, you get a total ordering. And we sort of saw this, let's say, hinted at when we looked at m equals 3 earlier, right? We saw that we needed on the extremal ray up here, you only needed 2 minimal generators, 3 and something else. But in the interior, you needed 3 minimal generators, essentially 1 in each equivalence class mod 3. And so now we see that actually reflected in the Kunz poset corresponding to each face, right? In particular, the number of atoms in this poset is essentially telling us how many minimal generators the semigroup needs to have in addition to m. All right, so here's m equals 4. We can have this quadrilateral cross section here. We got a bunch of Kunz posets here labeling some of the faces. And so you might notice that there's a couple of faces, in particular this back ray and this front ray here, that don't have posets labeling them. That's because those rays have no numerical semigroups on them. That turned out to be kind of an interesting tangent that we won't talk about in the talk here today, but some of the faces end up not containing any points that correspond to numerical semigroups. And there's turns out there's sort of good structural reasons for this to happen. There still ends up being a way to associate a poset to each of these faces in a way that's sort of consistent with the ones that already have labels. So from like a purely combinatorial perspective of this is a polyhedral cone, I would like all of its faces to have posets on them, not just some of them. There is a sort of satisfying way to resolve this the lack of semigroups there. But that's a topic for another talk. Another thing I'll point out here, as we move sort of down in dimension and with the faces, we see that our poset is gaining relations, right? So in some sense, the poset for the interior, this will always be a claw poset. You're going to have 0 as your unique minimal element, and then the rest are all just sit directly above 0 as atoms. This, say, facet back here puts 2 above 3. And if we move from that facet down to this ray, which is contained inside of there, now we end up with 1 on top of 2. So we end up with this total ordering, right? So as we sort of move from a face down to a face properly contained in it, our poset is gaining relations, in particular because it is now contained in strictly more facets, right? Like this one, we have 2 is above 3 because it's contained in this facet, and 1 is above both 2 and 3 because it's also contained in this facet. So that's how we're getting sort of this ray is the intersection of this back facet and this front facet. All right, so the TLDR here, the poset structure is sort of telling us combinatorial information about the face structure of the cone. So we asked a question and we answered it, right? When do two semigroups lie in sort of the interior of the same face of the cone? The answer was when they have the same poset. But if we think back philosophically to why we were asking this question, we wanted the geometric structure of this cone to tell us how we should be studying numerical semigroups. And so what this is telling us philosophically is that the Kunz poset should be a really important thing when studying numerical semigroups. So what properties of the semigroup can we read off of this poset? So one we sort of hinted at on the previous slide, the number of minimal generators of the semigroup is always going to be one more than the number of atoms of the poset, right? In particular, each atom down here, so okay, each element of the poset corresponds to an apiary set element. And any element here that is not an atom of the poset can be written as a sum of things down here, right? The A7 is going to be A2 plus A5. A1 is going to be A2 plus 2 copies of A5, right? And so the fact that these are atoms in the poset tells us that A2, A3, and A5, those apiary set elements, are going to be minimal generators of the corresponding semigroup. The +1 here is coming from the fact that M, which in this case is 13, has to also be a minimal generator. So your minimal generators are M plus one more generator for each atom of the Kunz poset. The number of maximal elements of your poset actually turns out to have interesting meaning as well, is what we call the Cohen-Macaulay type of S. This is reaching a bit more into the commutative algebra realm of things. There's a toric ideal hiding in the background of any numerical semigroup. We'll talk about that actually in a little bit, but the Cohen-Macaulay type of that ideal turns out to correspond to the number of maximal elements of the Kunz poset. All right. How about adjectives? So it's not uncommon when studying numerical semigroups to look at certain families of numerical semigroups. It turns out, sort of in general, numerical semigroups are really wild in terms of variability. And so if you want to make headway on sort of proving things, a lot of times you have to sort of specialize to a certain family, or at the very least, if you're studying a new quantity, it's better to start by studying it for families of numerical semigroups that we sort of know more about or have more structural stuff. And so there's a lot of adjectives in the numerical semigroups literature to sort of specify different families. One that comes up a lot is symmetric numerical semigroups. For the sort of more algebraically inclined here, that is when the corresponding toric ideal is Gorenstein. Well, so what does symmetric mean? From a semigroup perspective, here's how to think about it. So here I've got the semigroup generated by 4 and 7, and I've marked the number line with filled in black circles for the elements of S. Remember, we've got 4, 7, 8, etc. And the sort of red holes that are here are the gaps, right? So like we have 4 and 7 are in S, but 5 and 6 are not. And so visually here, if you take the locations, I actually don't know if my camera's flipped or not. If you take the locations of the elements, flip it this way, and place what was 0 at the Frobenius number, you get exactly the locations of the gaps. That's what it means to be symmetric. The locations of the elements, sort of measured away from 0, are exactly the locations of the gaps measured down from the Frobenius number. It turns out this shows up in the poset as exactly when the Kunz poset is self-dual. So for the sort of algebraically inclined in the audience, Gorenstein is equivalent to having Cohen-Macaulay type 1, which means you have a unique maximal element. So in some sense, this is the only case where you'd have a hope of your poset being self-dual, because you have a unique minimal element, you better have a unique maximal element. And it turns out, in this case, you do actually get a self-dual poset. And essentially where that's coming from is that if you take, in this case, for this one, so this is the Kunz poset of this semigroup down here. If you take A7 and you subtract 7 from it, you end up at the Frobenius number of S. And so from that and some sort of careful set membership checks, you can verify that the Kunz poset comes out to be self-dual under this symmetric condition. So that's kind of nice. This sort of nice algebraic property ends up being reflected in the poset as a nice poset theoretic property. All right, so a couple other adjectives here, families of semigroups that come up a lot. Complete intersection. There's an example here on the left. This again is sort of coming from the commutative algebra side of things. Complete intersection, toric ideals are nice, and algebraic things are nice in a lot of ways. It turns out there's a really nice description of when a numerical semigroup is complete intersection. It has to do with something called gluing. I won't talk about that today, but these posets have this really nice sort of Cartesian product structure, it turns out. This other family here, generalized arithmetical numerical semigroups. So what's really sort of at the heart of these, if your generating set for the semigroup is an arithmetic sequence, let's say 5, 7, 9, 11, something like this, then the Kunz poset ends up having a really nice graded structure. Particularly this one, let's see, the minimal generators, I think this is like 15, 17, 19, 21, 23. That's it. Because in particular, M has to be 15, and then generators are going to be 2, 4, 6, and 8 mod 15. And so that generating set will give you this poset. And so it turns out there's sort of a nice description of the faces of the Kunz cone that contain those semigroups, and in fact of the other semigroups that show up in those faces. Yeah, so sort of each of these adjectives ends up each face of the cone either consists entirely of semigroups in that family or contains none of them. So it's sort of a nice thing. All right, I want to talk a little bit about the commutative algebra side of things. I know this is a combinatorics seminar, but one of the nice things about this Kunz poset structure is that, as I'll talk about in a little bit here, some of the things that are typically very algebraic questions, even the ones that are sort of combinatorial in flavor, end up becoming sort of purely poset theoretic once we start looking at Kunz posets. And so I want to kind of give you an idea of what those look like. So as I sort of hinted at before, behind every numerical semigroup, there hides a toric ideal. The way we get this ideal, we're going to look at the ring homomorphism from a polynomial ring with one variable for each generator of the semigroup into the polynomial ring with one variable where each xi is sent to t to the power of whatever that corresponding generator is. So we're going to look at the kernel of that ring homomorphism. That's going to be some ideal. And in particular, it's going to be generated by differences of monomials. And there's a nice way to think about each of those differences of monomials in sort of semigroup land. So for example here, x is being sent to t to the 6th, y is being sent to t to the 9th. So in particular, x cubed and y squared are both getting sent under this map to t to the 18th, right? If we think back, we said 18 was the first element of the McNugget semigroup that we can get as a sum of generators in two different ways, as 3 copies of 6 or as 2 copies of 9. And so this difference of monomials being in the kernel of this map is exactly recording that 3 6-packs give you the same number of McNuggets as 2 9-packs. This other generator here is coming from 2 different ways to buy exactly 60 chicken nuggets. The easiest way is just to buy 3 packs of 20 to get your 60 McNuggets. A more complicated way would be 4 packs of 6 and 4 packs of 9. Both of those give you exactly 60 chicken McNuggets, and so that binomial lives in the ideal. Now, what does it mean for these 2 binomials to generate the ideal? This turns out to be essentially a graph theoretic question. What you need is that if someone walks up to you on the street, hands you a number of McNuggets, even if it's big, like 1,000,001 chicken McNuggets, and they hand you two different ways to purchase exactly 1,000,001 chicken McNuggets, there needs to be a way to get from one way of purchasing that many to the other by repeatedly in some fashion, either replacing 3 6-packs with 2 9-packs, right, which preserves the number of McNuggets you're purchasing, or swapping out 4 6-packs and 4 9-packs for 3 20-packs, right? So you can think of each of these as kind of being like a move from one combination of packs to another. And what you want is that if you sort of build a graph where each vertex is a way of buying 1,000,001 McNuggets, and you draw an edge whenever you get between two of those by replacing 3 6s with 2 9s, or 4 6s and 4 9s for 3 20s, you want that graph to be connected. There's some way to get between those. Now, why that's equivalent requires sort of playing with the algebra to kind of work through things, but I promise you that's what this means. And in particular, these two generators are enough to be able to do that for no matter what value 1,000,001 is the point. No matter what element of here you take, those two kind of moves let you get between any two ways of buying that particular number of McNuggets. And so at the end of the day, determining the minimal generating set here comes down to a graph theoretic question. And so that already feels kind of, or it certainly feels combinatorial, but but there's still sort of, there's still algebra that one has to kind of play with in some fashion. If we look at what this looks like in the realm of Kunz posetsets. So here we've got these two, and by the way, so what we call each of these in semigroup land is a trade, right? Here we're trading 3 6s for 2 9s. Here we'd be trading 3 20s for 4 6s and 4 9s. And we call, because these form a minimal generating set for the ideal, we call these a collection of minimal trades. So there's 2 minimal trades here. If we think about where these elements are, so this was the element 18, right, a traded element 18. Here this was at the element 60. Neither of those live in the apiary set, but they're really close to being in the apiary set, right? In particular, 18 was 9 plus 9, and 60 is 20 plus 20 plus 20. So they're not in the apiary set, but they're just outside of it. And so it turns out, if one sort of studies the poset structure here, there is just enough information in the poset to tell us exactly where each of these minimal trades needs to occur. So on the left one here, if we have a semigroup, numerical semigroup with this Kunz poset, there end up being exactly 5 minimal trades. So this toric ideal has exactly 5 minimal generators, and they will happen or the image of each of those will, each monomial gets sent to t to the, like, something corresponding to the semigroup element. And so it's telling you exactly where those things live. They're always sort of just barely outside the poset. If we take kind of a deep, closer look at this example here, right? Let's suppose someone walked up to you on the street, just handed you this Kunz poset. They told you they had behind their back a numerical semigroup whose Kunz poset was this one, but they didn't tell you what it was. Let's see what we can recover from there. Well, M has to be 10, so that has to be our first generator. We know there's going to be 3 other minimal generators, 2, 3, and 4 mod 10 respectively. So we can label them sort of, this is what they'd be called in the apiary set. And it turns out the toric ideal is going to have 4 binomial generators. One of them actually does happen in the apiary set. In particular, the apiary set element A6 can be written as A3 plus A3 or as A2 plus A4. There's 2 different ways to get to the same element. And so that gives us this binomial generator. The other 3 all live outside. And so what ends up happening here, so I've labeled the variables sort of carefully here. X2, X3, and X4 each correspond to one of these minimal generators that's not 10. And I'm using Y to denote the one that corresponds to 10. And so if we think about, let's for instance think about this sort of 4 that's out here. So if we take A2 plus A2, that gives us something not in the apiary set, right? But it definitely gives us something that's 4 mod 10, right? So that means this as an element of the semigroup is in the same equivalence class as A4, but it's strictly larger, right? So we can get from A4 up to here by adding a bunch of copies of 10. How many, we don't know, but adding some number of copies of 10 to A4 gives you whatever this element is. And that is essentially what's encoded here, right? 2 copies of A2 is going to give us the same element of S as A4 plus some mystery number of copies of 10. And so in this way, we're kind of recovering from each of these faded elements out here that we've added to the post set. We're recovering one of these minimal trades. And it turns out you can do this in a way that it will give you a minimal generating set. The only thing you can't recover from the post set is how many copies of Y you need in each of these. However, what turns out to be kind of nice, each of these mystery exponents is a linear function of A2, A3, and A4 in this case. And so if you think about, so S is some semigroup that lives in whatever face of C10. If you sort of move S and change it to a different semigroup in that same face, the Kunz post set stays the same. So the structure of this generating set stays the same. The only thing that changes is that these exponents are going to be varying as linear functions of whatever this A2, A3, and A4 are. And particularly, these were sort of coordinates of the corresponding point in the cone. All right, so just a couple of things I'll mention here, getting sort of more into the algebra side of things. Suppose minimal generating sets of toric ideals wasn't enough. Maybe you want homological information. You're interested in studying Betty numbers. Maybe you even want to get your hands on free resolutions. Well, it turns out there's a way, so for any toric ideal coming from a numerical semigroup, there's a way to write down a minimal free resolution of that toric ideal in such a way that if you change S to some other semigroup in the same face, all that changes in the structure of your resolution is when each of these exponents is going to be sort of changing as a linear function of the apiary set. Maybe free resolutions aren't even enough. Maybe you want to look at the infinite resolution of the base field over the corresponding semigroup algebra. These are in general not very well understood. Infinite resolutions are very, very complicated. But even then, there's going to be a way to write down an infinite free resolution for the base field over the semigroup algebra corresponding to the semigroup S, with this property that as you change S to other semigroups in the same face, all that you have to change in your resolution is some of the exponents on the y's. So yeah, this is, in particular, there's enough information in the Kunz post set, this nice finite post set, to determine an infinite free resolution up to the exponents on a few of these things. So the combinatorial structure of this resolution and the matrices and where the entries are non-zero and all that stuff is determined just by the post set. All right. I won't say more about the homological side of things, but there's a lot of interesting things to unpack there, and this is probably the area of things that's still the most open in some sense. The proof that you can build these infinite resolutions is non-constructive. And so it would be really nice, for instance, to have like a combinatorial way to build these things, like sort of post set theoretic. But at this point, we don't know how to do that yet. All right. I have a couple of other things I wanted to mention, or at least one other thing I wanted to mention as far as what we've sort of used this machinery for, right? So on this slide here, we saw a bunch of different properties of the numerical semigroup that we can read off either entirely or at least mostly from the Kunz post set. So that's sort of nice. But it would also be nice if we could use this post set structure to make headway on some sort of fundamental questions. So one of the ones where we've had a lot of luck with this is the following. Suppose you're told a given numerical semigroup has smallest generator M and exactly k minimal generators, and you want to know what are the possible number of minimal trays, so the number of minimal toric generators. Now, I'll mention real quick, if we didn't fix M, if all we fixed was K, the number of minimal generators, then this question has sort of a known answer. If K is 3, okay, so if K is 2, there's only this idealist principle. Fine. If K is 3, this ideal has either 2 or 3 minimal generators. Those are the only possibilities. That turns out to exactly distinguish the complete intersection and non-complete intersection cases, and is really sort of well understood in some sense what each of those have to look like. But once K is 4, this can have arbitrarily many generators, anywhere from 3 on up to as high as you want. It's always finite, something Noetherian-ness, but that number of minimal generators can be arbitrarily large once K is 4. But once you fix M, there's now an upper bound on how many generators there are here. So let me show you a table. Each row here corresponds to a value of M. So for instance, when M is 6, and so each entry in a box here is a possible number of minimal toric generators. So if M is 6, the toric ideal corresponding to S, it's possible to have exactly 6 minimal generators, exactly 9 toric generators, but it cannot have exactly 7 or exactly 8 if M is exactly 6. For each of these, let's say M is 6, the largest number of trades you can have is M choose 2. That's why we get 15 out here. And in fact, that is exactly, it's understood which semigroups hit that upper bound. They're known as max embedding dimension. But which numbers of minimal trades below that are possible is very much an open question. So if over the top of this, we sort of overlay information about K. So let's say M is 11, and we have exactly 5 minimal generators, then it is possible to have the number of minimal trades, number of toric generators, to be anywhere between 5 and 12. So it restricts you to that interval. If we move up a little bit, let's say M is 13, and we have 7 minimal generators, now we get something that looks a little bit, so we can have anywhere between 15 and 23 toric generators, or exactly 25 toric generators, but we cannot have exactly 24. By the way, all of this data so far here is just coming from computation. In fact, this was computation that the Kunz cone essentially allowed us to do, right? Let's say for M equals 6, I wanted to compute exactly what this full list of values is. Well, the Kunz cone for M equals 6, that's a 5-dimensional cone. It has a finite number of faces. It's a lot, but it's a finite number of faces. Each face has a corresponding Kunz poset, and all the semigroups in that face, their corresponding toric ideal is going to have the same number of minimal toric generators, somehow read off of the poset. So all we have to do is use something like normalites to compute all of the faces of C6. For each one, pick our favorite semigroup in there, or even not even do that necessarily. Build the Kunz poset from the facet description of that face, and go through that sort of poset construction on the previous slide to find out how many toric generators there are, and just do this for each face. You get a finite list of values. It turns out that's these values. All right. Now, as far as proving theorems, here's what was originally known about which of these values are a number of toric generators are possible. So there's, let's say, sort of folklore information. As we said, the largest number you can have is always going to be M choose 2, and it's known exactly which semigroups hit that upper bound. And when K is 3, you get this nice, you can only have 2 or 3 toric generators, and both of those cases, again, are really well understood in some fashion. There's a couple of papers from the late 90s and early 2000s that looked at this question. One of them was able to produce a family that went sort of straight down each of these columns from the top of each of these kind of mountaintops. So like the 15s going all down here, there was a particular family of semigroups that was produced for each given value of M and K that had exactly such that this is E choose or K choose 2 toric generators. And keep in mind the proof of that was actually somewhat complicated because if someone walks up to you on the street and hands you a numerical semigroup and says, how many minimal trades does this have? Right? How many toric generators does that toric ideal have? Essentially, the only way to do that, at least up until recently, was to actually like write down a minimal generating set. That required writing down a bunch of differences of monomials. Then you had to prove that this was actually like a complete generating set. Those proofs were often very tedious and requiring a lot of casework and stuff because you had to verify that no generators were missing. So that was one paper produced like sort of each of these kind of columns. Another paper looked at just the top of each of these mountains, so the top 3 rows here. And they were able to prove, one, that like each of these, let's say 6 filled in values here was possible to achieve. And they proved that you couldn't sort of escape out the left or right side. So if k equals 7 and m is somewhere between 7 and 9, they proved that you cannot have more than 21 minimal trades. And you can't have, so like in this row here, you can't have less than 20. In this row, you can't have less than 19. Their proof for this third case here involved a lot of casework. And they even had a line in the exposition there where they said, we conjecture that like if you go one more row down, these 5 are the ones that are possible. But given the extensive casework needed for this proof, some other kind of machinery is going to be needed to try to approach this next case or sort of subsequent ones. It turns out Kunz posets are such a machinery. So using this Kunz poset machinery, we were able to produce families of semigroups that hit every filled in value you see here. So for instance, if m is 14 and you wanted to have exactly 16 minimal trades, we found a family that does this for k equals 7 and a family for k equals 6 that has exactly 16 minimal traits. And one of the reasons we were able to do this is if all you're interested in is the number of minimal trades, you don't actually have to look at trades. All you have to look at is the Kunz poset, right? And I'll skip back to a picture here. You have to be able to figure out where these each of these trades lives and then count. And that's purely poset theoretic, figuring out where those live. And so that allows us to fill all these things in. We also were able to produce some bounds. So for instance, we produced a lower bound that essentially follows this perfect over, down, over, down, over, down staircase. And so like for k equals 7, for instance, this first row, you can't have less than 21. Here you can't have less than 20. Our bound is sharp all the way down to the 12 down here. But our bound ends up being weak starting here, because if you sort of kept going, would say that, again, if k is 7, and in this case m is 17, our lower bound says you can't have less than 11 minimal trades. But it turns out you can't even have 11. The lowest you can have is 12. But so we really give kind of a lower bound that at least for the first several rows here is sharp. And all of this ends up being very poset theoretic arguments. One last thing, so those are the bounds. One last thing I'll mention here, if we look specifically at k equals 4, right? So remember, k equals 3 was really well understood. You just have this column of 2s and 3s here that are possible. K equals 4, that was the first time that you can have arbitrarily many toric generators. But once you fix m, there's then sort of an upper bound on how many there can be. We were able to produce a family that hit all of these values. And in particular, we conjecture that this hits all of them. We checked this computationally out to m equals circa 42 or 43. And our family hits every single possible value that's obtained up to there. But we weren't able to prove that this was actually an upper bound. Ideally, there'd be some kind of poset theoretic argument that argued that this was actually is a sharp upper bound on how many toric generators there can be there. All right. In the interest of time, I'm going to skip this last part here, but there are some nice sort of computational consequences here of the stuff as well. All right. Thank you all for listening. I did not mean to kill the share. I just wanted to be able to see people again. There we go.
All right, any questions for Chris? Oh, if not, let's click the clapping hands reaction one more time. All right.
One silly question, actually.
Oh, yeah.
What about this 23 that remained white? Couldn't you achieve it?
That is a great question. Yeah, this one, yeah. That's a good question. So our family essentially, you can think of it as start at the mountain peak. We can get everything straight down and then down to the left, basically up until, oh, sorry, we can get one to the right and we can go down to the left up until sort of the last value we get from the previous one. That's why there's exactly sort of one column of overlaps here. And so the first place that there's something that's missing is where you would have to together you have to move two to the right from the top of the mountain here, or you'd have to be sort of get sufficiently far coming from k equals 8 to get up to this, and neither of those quite reach. Now, one thing that does appear to happen here, so there's always a step down to the right of exactly 3. So you see it happening here, you see it here, you see it here. That will continue happening all the way out, essentially what we proved. It appears that like next, it's always going to be a step down of 2. And you see that here. You don't actually, you do see it here. I think for 4 you see it too. Okay. But what ends up happening, each further step to the right you take, for sufficiently large k, it'll be the same step size down, right? So step of 3, step of 2, the next step, I forget what it is. It's probably a step of, I think it's a step of 2, maybe. I actually don't know. I have to go back and look. But for large k, it will be the same step. But before that, you can have some weirdness that happens. And there's a really neat sort of additive combinatorics reason why this 24 isn't possible. Essentially, this 25 is sort of a coincidence is the wrong word, but like, what is this? This is m equals 13 and k equals 7. There ends up being a really nice choice of 7 equivalence classes, mod 13, that you can build a poset that like for other values of m should not be, the mod classes should not work out as perfectly as they do. And so there's one of the things at play here is like sort of additive combinatorics of equivalence classes, mod m.
Okay, thanks. Yeah, very interesting pattern here. Still not fully understood.
Bailey, do you know how to stop the recording?
Oh,
I
yeah.
don't see it. I don't see an option on my end.